I'm Tim Ventura, and we're joined today by Dr. Charles Buehler, the co-founder of Exodus Propulsion Technology and lead scientist and co-founder of NASA's Electrostatics and Surface Physics Laboratory at Kennedy Space Center. Dr. Buehler has a PhD in Condensed Matter Physics from Florida State University, which he received in 2000 while working on high-temperature superconductors at the National High Magnetic Field Laboratory. Dr. Buehler has experience working with electrostatic discharge and ESD safety for the Space Shuttle program, the International Space Station program, and the Hubble Space Telescope program. He was also a co-investigator for 3 NASA research announcements funded by the Mars Exploration Program and is currently working on NASA's DUST project, focusing on utilizing electrostatic methods to remove dust from personnel and equipment that will be sent to the moon through NASA's Constellation program. Dr. Buehler joins us today to discuss his independent research into field effect propulsion systems at Exodus Technologies, which have led to a patented new propulsion technology that requires no fuel or ejection mass to produce thrust. So just a quick note and disclaimer beforehand, all views and opinions expressed today are those of Dr. Buehler alone and do not reflect those of NASA or the United States government. So Charlie, welcome, sir. It is an honor and a pleasure to have you here today with me.
Well, thank you, Tim. Thanks for having me. I appreciate it.
Well, let me start out with the big news. Your team has built and patented a new type of propulsion device that is currently producing over 1 Earth gravity of force, uses no propellant, and in careful testing in hard vacuum, it indicates that the force generated is not based on known effects, such as ion, wind, or conventional electrostatic forces. So do you have kind of a short elevator pitch description that you can give us for what this is and how it works?
Sure. Essentially, what we've discovered is that systems that contained an asymmetry in either electrostatic pressure or some kind of electrostatic divergent field can give a system of a center of mass a non-zero force component. So what that basically means is that there is some underlying physics that can essentially place force on an object should those 2 constraints be met. So technically, those terms are called asymmetrical capacitors that have been around for quite a while, would fall in that category, but there are other types that would fall into that category. So that's the 10,000-foot pitch.
Yeah, 10,000-foot view.
Yeah.
Before we go further, we should acknowledge that claims about field effect propulsion surface regularly. These are something that come up, every couple of years. Someone comes out and says, look, I have something, and usually those can be attributed to experimental error or, again, well-explained forces like ion wind. So what I want to do is remind the audience that you have done careful design and testing with these issues in mind. You knew about this going into it. You have been working on this for several years. And I also want to point out and remind people that you are NASA's subject matter expert on electrostatics. So if anyone would know about conventional explanations for anomalous measurements, it would be you, right?
That's true. And going into this, we did not, expect electrostatics to be the answer. As I described before, we were looking at other types of momentum initially for, 20, 25 years or so. But nature has its own way of doing things, and our job is to uncover what nature does. It just happened to fall into my lap as what I'm the expert in. So we take that as it is. So.
Now, I do want to get into the patent. Again, this is fully patent protected. And the patent is entitled A System and Method for Generating Forces Using Asymmetrical Electrostatic Pressure. So this is your first patent on this technology, but I understand you have more on the way. And currently, as things stand, this is fully protected, not only based on what you've observed, but also the model that you've created to optimize it for propulsion applications, right?
Yeah, I think that's what makes this unique among other potential discoveries in this field is that we have a theory, we test to the theory, then the theory leads to a model, the model leads to computations, and then the engineering leads to the design. So you have to have those 3 things working in conjunction to have a to have a path forward, at least in my opinion. You want the theory, the modeling, and the experiment all to mesh. And that's what's unique about this. And that's what makes it very exciting. And that's what led to such a significant amount of progress in just a short amount of time. So, and we keep testing it every day to validate it. So it's right on track. So we think we have a good handle on it. So yes.
So the term, and again, this comes right out of the patent, the term asymmetric electrical pressure is similar to Thomas Townsend Brown's research into asymmetrical capacitors back in I think the 1950s, as well as effects observed earlier in antique Fizeau condensers, which have also been called the gravity capacitor. So what makes your device unique from these, and what led to it being patentable?
Well, I think what led it to be different in those older papers and that older subject matter is probably valid for most of the point. For most, it's unfair to say that it's not. However, without a theory back then to describe it, it was hard for them to miniaturize it, to optimize it, all of those things you want to do to make it a useful force. And like you said earlier, in doing so, when you're playing with high voltages, high fields, and asymmetrical capacitors, you're going to uncover things that are not the force that we're looking for, like ion wind thrusters and lifters and all these other things that certainly give forces, but not for the reasons that that we're looking for. So it's all mixed in there. It's all jumbled in there together. So without a sound approach, I think our patent stands out that tells you this is the effect, this is where it comes from. Now let's miniaturize it. And as I said before, the asymmetrical capacitor component of this, we're not building asymmetrical capacitors anymore, right? That's a geometry thing. But there are other ways to take advantage of the electrostatic pressure forces. The asymmetrical capacitors is a nice, handy, inexpensive way of doing that, but it's not the way we're moving forward with it. So that's captured in that patent, but also the follow-on patent.
I want to pop open the slide deck and show people one of the slides from your recent presentation. I'm going to put a link to this in the show notes, but I want to get into the propulsive forces. And I think this, for me, this was the part that blew me away. This is incredibly exciting. And this goes to what you were saying about optimizing it and building the model. So let me share that. So in terms of propulsive force, you have built several hundred experimental device variations. And between 2014 and 2021, and I think that this graph reflects that, they all produced what appears to be less than 1,000th of an Earth gravity of force. Now that changed in 2021, and you have rapidly increased up to slightly over 1G of force. So can you tell me what led to this dramatic increase in propulsive force output? And also, how much farther do you think you might be able to take this using current design technology?
Sure. So what we have here, like I said, is a graph of our progress. It doesn't represent all of the tests, and it certainly doesn't represent all of the models that we've tested. That's numbers close to 1,000. But here's a few select that we put together just to kind of show the highlight of the progress. So from 2016 to 2020, like I said, those are basically the conventional asymmetrical capacitors that you'd see in the textbooks. With a twist, we encased them, and I don't think they've ever been encased, in styrofoam to make sure that they didn't leak charge. We definitely did that on purpose, and they still worked. So that's kind of what sets us apart from the old T. Thomas Brown stuff. A lot of that stuff was in air with tens of thousands of volts. We shy away from that. We go to much lower voltage, and we try to encapsulate everything. The big advantage, the big jump in 2020, 2021 was a few things. The first thing was the presence of the high vacuum system. So now once we move things into high vacuum, now you can eliminate some of the sources of noise and errors, like the ion wind, any kind of gas discharge, corona discharge, glow discharge, brush discharge. You try to eliminate any kind of current leakage. Essentially current leakage. Anytime there's current in our system, the force goes away. So it's very odd. The second thing is the type of thrusters. We went away from the asymmetrical capacitor thrusters to kind of the two-dimensional thin film type. Okay, so we had different dielectrics sandwiched next to each other. That's a different way to make an asymmetrical field on one ground plate versus the other high voltage plate. It's a very simple way to do it. And that's also covered in the patents. So once we began to do that, one of the dielectrics was vacuum. And when you apply high enough voltage, the third thing that we learned, and probably the greatest thing that we learned, is that there's two types of charges, and each type of charge produces a different level of thrust. In electrostatics, the thrust is, there's two types of charges. There's called free charge and there's bound charge. So free charge is what's in a conductor, and bound charge is basically what's in an insulator, if you want to be plain about it. And what we discovered is that throughout all of the tests, even back to 2016, 2017, there have been mixtures of both. And we really didn't understand that till the 2020 tests that we performed. And once we understood that, that allowed us to make thrusters optimized to take advantage of the bound charge. So the bound charge, although it produces higher thrust, it's a little bit more difficult to manipulate because you're dealing with insulators. So, but that's kind of where we're headed now. That's kind of the direction that we're going into now. So now we're moving beyond thin films to more chemical battery-based type of thrusters where we actually can inject these charges directly instead of tribocharging or doing something, just by charge injection or induction charging. There are other ways to actually get that charge into the dielectrics.
So now just to ask, free charges, that would be kind of like electrons that are traveling in a wire, right? And bound charges would be electrons that are actually in an atom and they can't go anywhere.
Well, they'd be in a dielectric medium. So they're, they're embedded in a plastic or a epoxy or a Kevlar, any kind of insulator.
Oh, okay.
Styrofoam. So those are real charges too. Those are bound charges.
And I'm glad that we were able to put this slide up. And again, you did a very lengthy, detailed presentation on this. So people looking at the slide deck, they can see the slides on the left. You have incredible detail that you went through. I'm going to link to this in the notes for anyone who wants more information. And that way we can really just provide maximum value on what you have already described because it was so detailed in depth. But going back to the force output slide, this is what got me really excited. Now, years ago, I worked on lifters. I'm familiar with Biefeld-Brown. I even built a couple of failed gravity capacitor attempts back in the day. And so these dots down here, in the 1,000th of a G range, these are definitely representative of everything that was documented, up until very recently. And when I saw your graph, I saw this evolution of design that you've done, right? And I felt like they've dialed this in. It's like the model that you've created allowed you to start to optimize this. And as you dial that in, you can just watch those thrust outputs increase and increase and increase. And it almost looks like an exponential curve. So one thing I wanted to ask was, how far do you think you could take this with current technology in terms of gravities? And if, again, hypothetically speaking, if NASA handed you a blank check and said, you know what, do as much as you can, how far do you think that this could go with like the latest and greatest in terms of, material electronic components?
I think it can go quite far, to be honest. Right now, as I said, we're dealing with the battery world, so the chemical versions of these things. They're no longer thin films. They're basically liquids, essentially, that are applied to surfaces. So they're basically crappy batteries. And we're trying to optimize the chemistry to optimize the charge injection. And once we do that and apply our fields, we'll see our force. So that's why the force keeps getting higher and higher, because we are more microscopic. And as we become more microscopic, the mass of our system goes way down and our thrust stays pretty high. So that's what's exciting about it. Now, how far can we go? We're only doing DC. We haven't even done a lot of AC in these tests, which is pretty cool. We've done AC up to a few, megahertz or so, but the effect doesn't scale with frequency as you would expect because it's not photon based, it's field based. So, but we do know that there are other versions of our thrust that can take advantage of RF, and we will discuss those in the future as well. Once we prove them out, those are just theoretical. So the sky's the limit, really. How much bound charge can you fit in something? How much, if you think of a car battery, how much free charge is in a car battery? A lot of charge is in a car battery. A lot of a lot of current is stored in there. A lot of energy is stored in there. So right now we're just kind of optimizing that in a two-dimensional system, and then stacking it. So once we stack things, obviously the thrust goes way up. But this is the thrust per thruster mass. And the thruster mass is very, very thin, very, very small materials. They're not even metallic. So these things can get very, very light. And we're only, we're still baby stepping it because we're still in the DC world. So as we get higher and higher with the AC, we think there are other ways that AC can help us, not just the increasing our force, but also changing its direction. So theoretically, there's a lot more that we can root out. And that's kind of how we do this. That's kind of how we approach this. Well, if A works, B should work. And if B works, C should work. If C works, D should work. So we're just kind of going down the path. And so far, everything has, we've been lucky, knock on wood, everything following the physics. It's been just doing what it's supposed to do. If you say you're making a battery this way, or if you say you're making a thin film this way, if you say you're turbocharging an insulator that way, if you say you're microscopically etching a surface that way, or making an asymmetrical capacitor that way, you should get a certain amount of thrust. And we've seen that. So we're just basically just following the progression of the science. And where it tops out, I don't really know. I think we'll hit the breakdown of materials at some point where the materials just cannot pack up any more charge. We'll hit the dielectric strength of the insulators. That's bound to happen. We always test to breakdown. We're not making new materials for this. Okay, that's one thing. We're not inventing new materials. We're using common techniques and common materials, and we'll hit the limits there eventually. And then we'll have to move on to more sophisticated power systems. The AC part, the high frequency stuff. We'll move on to that. We may have to move on to things that are a little bit more elaborate, terahertz frequencies, those kinds of things. Those are all kind of on the docket, if you will. There's probably half a dozen things that we definitely like to explore if we had a blank check, and they'd be different doors, different ways of doing it. There's, we haven't knocked out all of them. We've got 6 or 8 that we want to explore. But right now we're doing what we can afford.
Yeah.
We're self-funded. So that really limits a lot of what what our progress is. But, give the credit to Drew. He is a workhorse. He works every day and he builds these every day. Tweaks them, builds them, tweaks them, tests them, tweaks them again, tests them. So the progress is really mostly due to him barreling through and then accomplishing the little steps, increment steps, day by day by day. But to answer your question, there's no upper limit, at least theoretically, right now that we know of, other than the breakdown of materials or whatnot. But we haven't even explored the AC version of it really thoroughly yet.
Well, I'll come back to the second. But let me put this slide up, though. I did want to show this. Again, this is from your slide presentation. This is just one series of tests, and this is 150 test runs with variations on them. So you mentioned Drew building these and testing these repeatedly. And, again, this is not as simple as people might think, because you guys are doing hard vacuum testing. So to take the vacuum chamber down to the required pressure, that takes time. It takes work. I know that Drew has been fighting with all sorts of, little machinery adjustments and tweaks and things like that. So there's a lot that goes into each one of these tests. And this is just 150. And as I understand things, this is just from a limited period of time. So you actually have probably far more tests that you've done overall, right?
We're in the thousands for sure. This is when we were doing tests once a week. Okay. The 3 test articles once a week. Now the tests are daily. So these were not vacuum tests, unfortunately. 2019 and prior, that was in air. So this is
okay.
This is him, machining, putting things in the mill, putting things in the lathe, heat sinks, styrofoam, T-blades, epoxy. These are the real old style asymmetrical capacitors.
Okay.
Heavy suckers. And they take a long time to make, but they still work. But they've led us to the physics that we are, that we have today, which is useful.
So going and again, going back to this thruster mass, and this is the chart that got me so excited. Before I take the slide deck down, I did want to mention, as I understand things, and I could be mistaken, but because this is DC and because it's capacitive in nature, I think that thrust or the propulsive force lasts as long as it is charged, right? And so
Correct.
if the I guess the takeaway that I had from that was the overall energy input is a lot less because you don't have to run constant energy through it. You can basically charge it like a capacitor, and as long as that charge remains, you will have this thrust. So, in terms of efficiency, this is a lot higher than even this chart might suggest.
Yeah, efficiency would be hard to describe mathematically. Um, the energy conservation over length of time is hard to rationalize. We have to prove that that is the case in space. Does this stay on forever? Right now, when we charge up these capacitors, even the old large heavy foam ones, we can charge them, turn it off, but there's charge that remains inside. So as the charge remains inside, that creates the field. As long as the field is there, the thrust is there. So we can see some of these things sit on a scale for days and they still have charge in them. They're still producing thrust. It's very hard to reconcile from a scientific point of view because it does seem to violate a lot of energy laws that we have. But this is fundamental. So understanding this will kind of get us an idea of what is the structure of space-time. What is it? Because it's interacting with it in a way we don't quite fully understand. So it's easy to make these things, and it's a tool for the scientific community to use to try to explore those hard questions, I think. And you can't deny this. There's not a lot to this. You're charging up Teflon and copper tape and foam, and you have this thrust. So it gives a nice way to do an inexpensive test, just like the lifters were for many years, to explain ion winds and all of that. The same kind of thing can be used in a classroom to describe whatever force the scientific community decides that this actually is. I think it's just a simple electric field because there's nothing else going on other than electric fields. There's no magnetic fields. It's DC. Is it warping space-time? Goodness, I can't imagine that it is. Maybe it is. I don't have the tools to check that interferometry or cesium clocks or something like that. That's far more elaborate than we've explored. But there is something to be said about having a field, an electric field in space, because no one knows what an electric field really is. But what happens if you have an asymmetrical electric field in space? What are its consequences? Well, it looks like force is one of its consequences. So this gets into the whole thing of the 0-point energy and all of that jazz. So
at this point, some of the audience may have concerns about conservation of energy. And again, this is something that you addressed in your presentation. Charging this up and having it produce propulsive force with kind of a standing charge, right? Where the energy is already put in, you're not putting in more energy. That make people nervous, I guess. But from what I understand, there may be relativistic explanations for this based on hidden momentum. There could also potentially be quantum mechanical explanations that are related to the Casimir effect, right? Those are two models that you talked about in the presentation.
So yeah, the hidden momentum is a relativistic effect that occurs when you have moving charges or you have magnetic fields. So anytime you have a current loop in any form or fashion, you'll have a hidden momentum. These static systems, I don't believe, have hidden momentum. Charges embedded into plastic, I don't believe, are moving relativistic speeds. People could argue with that, but I don't think there's a hidden momentum. The hidden momentum would give an impulse. It wouldn't give a sustained force because it's not changing with time. So I kind of rule out the hidden momentum. The Casimir force and all of that is, I think, is a great example, I think, of how you can use quantum mechanics and the quantum vacuum fluctuations to give you a net force on a system. Or even if it's a not net translation, it's a force of two plates. And that can easily be interpreted as pressure of the plates. Same math. So it's a model. It's there. The question is, how do we humans, we inject energy way above the vacuum energy, because that's where we are, way above it. Vacuum's way down here low. How do we take advantage of that low energy? And is that what's happening? It has to be what's happening, because we have interaction physics, we have scattering, we have Coulomb forces. We have, anytime you have a field, you'll have a force. Gravity doesn't turn off. Coulomb forces don't turn off. If I separate the charges, they don't just turn off because you want them to. This is another force that doesn't turn off because you want it to. So there is an interaction going on there. Microscopically, it's going to take a physicist much smarter than me probably to come up with that and derive all of that. But I think the QED is there. I think there's enough there that someone can look at that and say, well, this is probably what's happening. If you can explain how the Coulomb force stays on over a length of time, you could probably explain how this stays on over a length of time. All the matrix elements for the scattering are there developed. So it's something I'm looking on my spare time, but it takes a lot of time to redo QED.
Now, I understand that there are at least 2 outside groups that have verified this effect as well, in addition to, and again, this goes back to, we have decades of anecdotal stories of propulsive forces that you might almost call noise range, right? Where, like T.T. Brown, where he's like, okay, we have something, but it comes and goes. People have difficulty replicating it, the whole 9 yards. You have a couple verifications as well. So this isn't just your team. This is something that you're able to kind of group, I guess, a cluster of different verifications in with, right?
I would say so. I mean, we've known that once the patent came out, we know Mark's lab took it over and said, well, this is a picture of a heat sink in our patent. So we just took a computer heat sink and measure a force with that. It's that simple and it works. There's other examples out there. And even the 2-dimensional examples, there's some out there. So there's a lot of evidence out there for this. And there might be even others that we just haven't uncovered yet. Like I described, there's the EM drive, which I think can easily be explained with this physics. It's an RF version. We haven't done the RF version yet, but it makes a heck of a lot of sense. The Mach effect thruster, that could be, just based on its geometry and its voltage. It could be another example of this force that could be, the Mach effect might be real, but it could possibly be that this force is entangled with it or masks it, or vice versa. I don't know. But can't ignore this force. So you have to look at the world now. What I'm trying to get the scientific community is to look at this force now. Now put this in the context of what you know already. How does it fit in? How does it play in? And it can play a role in many things, even in a role in gravity, in dark energy and dark matter. When you look at the conservation of energy that I started with, that fluctuation of the E squared is not allowed to be 0. You cannot put 0 in there according to quantum mechanics. So there has to be some remnant energy, hence force density, that's acting on everything, everywhere. So what are its implications? That's not my theory. That people have come up with that 50 years ago. They probably just didn't know that they could take advantage of that for what we're doing when you go above the 0 point. So I think that's all we're doing. So that's what makes it exciting. I think it's a good opportunity for people to run these tests, look at them, watch them go in space, watch it move in space, and then say, well, what does it imply? What does it imply? What are the implications? How does it mess my experiment up? How does it describe this effect or that effect? Because that's usually what a discovery does. It starts opening a light on 20 other different things that the researcher didn't even think about looking at. And I think this electrostatic pressure divine force thing, it's incredibly weak, but it could explain maybe some big things without us knowing it. So until we know, we can't even think about testing something like this. But now we know this exists. Now we know it's real. What does it imply? What are its implications? How do we take advantage of them? Of course, our group and our friends at APEC want to make spaceships. That's what everyone wants to do. We want to get off the Earth. That's fantastic. It's a great use for this. But there could be others too. We could make energy out of the vacuum. You can make force, you can make energy. I haven't looked at how to do that yet. Not out of the question. Not something we spend a lot of time on. But someone will. Someone absolutely will. And we're here to help.
Well, again, Charlie, this is all tremendously exciting. This is, I view this as a major breakthrough, and this comes after hard work and diligent effort. I mean, you guys have done the work over a period of time to get here. You know, this isn't something that just appeared. And again, I mean, your credentials and the careful experimentation you've done have ruled out the common sources of error that have plagued this area for decades. So on that note, let me thank you so much for your time today. It has been a true pleasure and absolutely an honor to have you with me. Let me close by asking what comes next for this technology in the first few months of 2024?
First few months of 2024. Well, we're hoping to do some demos and space demos. That's what we're trying to get some funding to do. I think that would be useful. I think that would be a great way to show off the technology. At the same time, we're barreling through with the path that we're on now. And then if we can get some funding, we can move on to the other paths that I've mentioned. I don't know when we'll start those, but it depends on funding. So just keep posted, and we'll keep you informed on our progress.
Thank you again so much for your time today, sir.
Hey, no problem. Thank you, Tim.